All right, guys, today we are beginning our very last unit of the year. It's on differential equations. And differential equations we've already dealt with a little bit this year. It's when we have a derivative equation. And the goal of what it means to solve a differential equation is to find the original function that gives you that derivative. We're going to start with a warm-up of some differential equations you should already be able to solve. So here's this first one. Given that f prime of x equals e to the 3x plus sine of x, determine f of x. Notice, this is a differential equation because it's giving us a derivative function. This is telling us about the slopes of the original function. And so we can find the original functions. If it doesn't specify an initial condition, differential equations will often have a plus c as part of their answers. And it just means that there's a whole bunch of different functions that could all have these same slopes. So what is f of x? Well, hopefully we recognize that to find f of x, all we need to do is do the antiderivative. Here, e to the 3x, it's not just e to the x, we have a u in here. U is 3x, and so du is 3. When du is just a constant, we're just going to need to divide by the 3. So it's going to be 1/3. The integral of e to the x is e to the x, so the integral of e to the 3x is going to be e to the 3x. You could have done this by putting e to the u and then substituting back in and doing that, but I'm just doing the integral kind of in my head here. And the integral of sine of x is cosine of x, but we need to make sure it doesn't have a negative on it. The derivative of cosine of x is negative sine of x, and so we need a negative here. That way when we do the derivative, it'll give us positive sine of x, and we always need a plus c. So this is a set of equations. Any value of c we could put in here would all give us a function that when we do the derivative has these slopes. So this is the set of slopes for a whole bunch of different functions, and this is the solution to a differential equation. Hopefully we feel good about that. One thing you could do is check to see, is it a solution? By doing the derivative. So if we did the derivative here, f prime of x equals, here's a constant, we would leave the constant alone, and we would do the derivative of e to the 3x is e to the 3x times the derivative of the inside because of the chain rule, so times 3. The derivative of cosine of x is negative sine of x, so we end up with plus sine of x, and the derivative of a constant would be 0, and you'll see that 3 times 1/3 will just be this. And this is what the original derivative was. So we can always check to see if something is the solution to a differential equation by doing the derivative of it and checking it that way. That can come up on the multiple choice portion of the AP exam because you might want to check to see, is something a solution to a differential equation? We'll just do the derivative of it, and if it gives you that derivative, it could be a solution. Okay. The second one, if the velocity of a particle is given by this, determine the position function. Given that the initial condition of the position, s of 2 equals -4. Now, again, this is a differential equation because this velocity is the derivative of position. So it's asking you to find the original position function given the derivative. Go ahead and do that. What is v of t? Make sure you use this initial condition. Well, s of t will be the integral of v of t. And so here, clearly there is a u that is t cubed plus 1. There's an inside function. And so this is, and the derivative, du, would be 3t squared. Here I'll actually do a substitution. So this is going to be the integral of u to the 1/2 power. I'm going to rewrite square root as to the 1/2 power. Du, the derivative of the inside function was just right there. That is the derivative. There it is. And so let's see, we need to raise the power by 1. So 1/2 plus 2/2 is 1, so raising the power by 1. And then divide by that power. Dividing by 3/2 is multiplying by the reciprocal, plus c. And I'm going to plug that back in. So 2/3, u was t cubed plus 1. This is the square root of t cubed plus 1 cubed plus c. That's the original, that's all the possible antiderivatives of this, but they also gave us an initial condition, s of 2 equals -4. And so when I plug in t is 2, I need to get -4 out. So we're going to use this to solve for c. When I plug in 2 cubed, 2 times 2 times 2 is 8. 8 plus 1 is 9. Square root of 9 is 3. 3 to the 3rd power is 27. 27 divided by, so 2/3 is dividing by 3 and then multiplying by 2. So 27 divided by 3 is 9. 9 times 2 is 18. You don't have to do all of those steps at once, obviously. So C is, we subtract 18, negative 22. And so the solution to the differential equation is when we have a particular, when we have an initial condition, we can find what the C is, and this will be the solution to the differential equation that both has slopes, the velocities of this position function are this, and the initial condition is also met. So if we're given an initial condition, this is an initial condition, then we can find not just the general solution, this would be the general solution, like we found in number 1, we can also find the particular solution that matches the original thing. Okay, here we've got a different one. We've got f prime prime of x equals e to the x, and we want to determine f of x. This is a second derivative, and we want to find the original function. Go ahead and try to find that. Hopefully, you started by finding the first derivative and the integral by doing the antiderivative. The antiderivative of e to the x is e to the x. The antiderivative of this is a power rule. This is x to the negative 2 power, and so it's going to be we raise the power by 1, so it's going to be x to the negative 1 power, and divide by that new power. So dividing by negative 1 makes it negative. The antiderivative of 4 is 4x, and we need a plus c. Now, I could rewrite this as 1 over x, and I would if this was going to be my final solution, and maybe I will. Okay, let's just do that. It's e to the x minus 1 over x plus 4x plus c, but this is not my final solution because we need to go back and find the original function. So f of x equals the integral of e to the x is e to the x. The antiderivative of 1 over x is natural log of absolute value of x. Be careful, not a power rule one. So this one that looked very similar to it was a power rule, but 1 over x is a special one, that's natural log. Here we need to raise the power by 1 and divide by the power. And c is a constant. It will now have that constant times x plus another c. So I'm going to call this C1 and C2. There's one constant times x that when you take the derivative will give you a constant, and then when you take the derivative again will go away and become 0. And then this one is another constant we could have. So it's this whole family of solutions that could be the original one. All functions of this form will have a second derivative of this. Okay, so there's a whole bunch of different possible solutions. All right. Let's see, the slope of a curve given by 2x minus 5, here's the slope. So this should be a way of telling you that this is the derivative. So it's saying f prime at any x, the slope at any x is given by 2x minus 5. So this is telling you a derivative. The slope, we need to know that's a derivative, right? Determine the equation of the curve, so the original function, if the curve passes through negative 1, 4. This is an initial condition. So what is the original function if the slope is 2x minus 5 and it goes through negative 1, 4? Well, here's the slopes. We can find the original functions based on that by doing the antiderivative. So x squared minus 5x plus c. But again, we've got the initial condition here. So we're going to plug in 4 for y and plug in negative 1 for x. So negative 1 squared minus 5 times negative 1 plus c. 4 equals 1 plus 5 plus c. This is 6, so I'm going to subtract 6 and get c is negative 2. We're going to then rewrite the original function with the c plugged in. So x squared minus 5x minus 2, there is the original function that has that initial condition. This is the solution to the differential equation. All right, the acceleration of a particle is given by a of t equals this. Determine the velocity. Okay, now the velocity is the derivative of position, but acceleration is the derivative of velocity. It's how much is the velocity changing by. And so this is a differential equation that's asking us to find the original function if the initial velocity is 5 units per second. Initial velocity is telling us that the velocity at time equals 0 is 5. So initial velocity means time equals 0. Okay, so what is the velocity function? Okay, well, this is the derivative of velocity, acceleration, so we need to find the antiderivative, and this one looks tricky, right? clearly we need to use some substitution somewhere. And I notice it's e to the something power. And I kind of want to rewrite this. I'm going to rewrite this as a of t equals e to the tangent of t times 1 over cosine squared of t. I find it really helpful when there's a fraction to write it as a multiplication by a reciprocal. I think that's really useful sometimes. And now I hope we can see that there is a, I don't have a red pen here with me. I don't have a red pen. Did I have one earlier? Oh, here it is. Okay. I hope we can see that if we say that u equals tangent of t, because it's the inside function inside of e to the something, then du would be, the derivative of tangent is secant squared of t. Now, is this secant squared? Yes. Secant squared is 1 over cosine squared of t. So this is du. Oh man, this pen is crappy. Okay, so we actually just have a of t equals e to the u du. And so we can just find the velocity. We can do the antiderivative. The antiderivative of e to the something is just e to the something plus c. And so the velocity, I guess this is velocity of u rather than t, is equal to e to the, u was tangent of t, plus c. Now, the initial velocity is 5 units per second. So the velocity is going to be 5 when the time is 0. And tangent of 0 is 0. E to the 0 power is 1. And so 5 equals 1 plus c. So c is 4. And we can plug that back in. So v of t equals e to the tangent of t plus 4. That will give us a derivative, an acceleration that matches this. And I hope you can see it now, right? You can do the derivative. The derivative of e to the tangent of t is going to be e to the tangent of t times the derivative of tangent, which is 1 over cosine squared, secant squared. And when we plug in 0, the initial velocity will be 5. Okay, last one. Solve, given that f of e equals 3 and f prime of x equals 5 over x. Well, hopefully we can see that this is 5 times 1 over x. And so f of x is going to equal 5 times natural log of absolute value of x plus c. And when x is e, the y value needs to be 3. So 3 equals 5 natural log of e plus c. You'll notice I got rid of the absolute value bars here because the absolute value of e is e. Absolute value just changes something positive. So with x, we don't know if it's a positive or a negative, so we need to leave the absolute value there. But with e is a positive number. It's like 2.7182818284590, whatever. But it's positive, so the absolute value is just e. And the natural log of e is saying e to what power gets you e? And e to the 1 power gets you e. So this is 3 equals 5 times 1, which is 5, plus c. So c is -2. We just subtract. So plugging back in, f of x equals 5 natural log absolute value of x minus 2. So that was a ton of differential equations you already had access to. That's not new. We already were able to find antiderivatives, and so we already could find a lot of differential equations and solve them. Today, the new stuff we're going to talk about, and we've talked a little bit about this before, we're going to start by talking about slope fields. A cool thing you can do with differential equations is remember, it's something that tells you what the derivative is equal to. Where is the slope? And, you know, if you can find the slope at every point, then you can graph what the function looks like. So I'm going to give you an example here. And so dy dx equals, notice this one just has x's in it. And so I can put in any x value and it will tell me the slope at that x value. So for instance, I put in x equals 0. So when x equals 0, the slope will be 1/2 of 0 plus 1 will be slope equals 1, right? So when x equals 0, the slope is 1. Now, does this match this? What slope? I hope we recognize what slope this one is. What is the slope here at x equals 0? This is a slope of 0 if it's a horizontal line. Horizontal lines have a slope of 0. So this doesn't match that at x equals 0, the slope is 1. On the other hand, this one has a slope that is 1 at all the x values of 0. Notice that it's a whole bunch of different curves here. And the reason it's a bunch of different curves is because when you do the antiderivative of this will be 1/4 x squared plus x plus c. The plus c will give you different y-intercepts. And so a lot of times with slope fields, all the time with slope fields, you'll have a bunch of different curves depending on what the plus c is. But they will all match that at x equals 0, y prime is 1. And we'll notice that that's the only one. Like here, when x is 0, the slopes are not all 1. Here at x equals 0, okay, the slope is 1 here, but the slope isn't 1 here. And this is also an x equals 0 point. So this one has to be b, because at x equals 0, the slope is 1. Now, this one has both an x and a y. So instead of just choosing what the value of x is, we need to choose a point for x and y. And I usually like just picking easy points, like when x is 0 and y is 0, what is y prime? Well, when x is 0 and y is 0, y prime will be 0. So I need to find a function that when x is 0 and y is 0, the slope is 0. And then this type of graphing program didn't do a good job of like rendering the x-axis. So it's actually kind of hard to tell on the x-axis what's going on. Like maybe this one has a slope of 0, maybe this one has a slope of 0, maybe this one has a slope of 0. Let's pick a different point. Let's pick when x is 1 and y is 1. When x is 1 and y is 1, 1 minus 1 is 0. And so y prime will also be 0 at the point 1, 1. So let's look at the point 1, 1. Is this slope 0? No. At the point 1, 1, is this slope 0? Yes, this slope is 0. At the point 1, 1, is this slope 0? No, this is a slope of 1. And so this is the only one that matches. Sometimes you need to pick more than one point to check. Like, let's say there had been 3 of them that had a slope of 0. Well, then I'd pick another point. Like maybe I would pick, I don't know, -1, 1, like put in a negative number and see what happens. If I put in x is -1 and y is 1, the slope needs to be -2. And so check it out. When I go to -1, 1, does that slope look like it could be -2? I sure hope so. Like, yeah, sure, y prime equals -2 there. So you can just plug in a point at each point to see what the slope is. All right, so this one's gonna be C. I want you guys to try this one on, actually try this one on your own. Which one of these graphs matches up, and it could be a repeat, right? Which one of these graphs matches up with the slope is equal to -x over y? And hopefully you just picked a point, like, okay, pick, you know, when x is 1, y is 1, when you put in 1, 1, 1 for x and 1 for y, the slope is -1. So let's see, when x is 1 and y is 1, the slope is not -1. When x is 1 and y is 1, the slope is not -1. The slope is not -1. But when x is 1 and y is 1 here, this one has a slope of -1, and so this is going to be the one that matches. And I could check more points on it if I wanted to. Maybe you should do that. Check like when x is 3 and y is 1, right? Like what's the slope going to be? Well, when x is 3 and y is 1, the slope is -3. It's a steep negative. So that's what works. And verify for yourself which one is dy dx equals y. Pick a point. So all the slopes will be the same at every y. So like when y equals 1, the slope will be 1, right? So when y is 1, the slope is 1. When y is 2, the slope is 2. When y is -1, the slopes are all -1. So this one is D. All right, guys, so slope fields are just a graph of the slopes, and they can let us see, like, oh, if we know what the slopes are, we can see what the functions are. Sometimes they're really easy ones to solve. Like we could have solved this and gotten 1/4 x squared plus x plus c. That's what all these parabolas are. All of these are different parabolas. But sometimes it'll come out to be like, these are circles. And depending on what c is, the circle will have a different radius. So that's cool. This one has a bunch of different, looks like exponential functions, right? Where depending on what the c is, you know, it's shifted differently. So that's cool. Okay, but we can kind of tell what function it is based on what the slopes are. That's neat. Let's look at how we can solve these things. First, let's graph this differential equation. And every once in a while in the AP exam, they ask us to graph a differential equation. And what we're going to do is we're going to just pick it'll tell us what points to graph it at. And we're gonna pick, I think we'll pick these points to graph. We will do these ones today for what our purposes are. And we would normally do this as a class where different people would calculate different ones, so we wouldn't have to all do so many. Okay, let's see. When x is 0, this point is at 0, 1. And so we're going to graph the slope by putting in x is 0 and y is 1. At 0, 1, dy dx at 0, 1. When we plug in 0, 1, we get 0, negative 0 over 1, but that's just 0, equals 0. So at the point 0, 1, the slope is 0. And in fact, at all places where x is 0. Like, it makes it a lot faster if we recognize that everywhere where x is 0, the slopes will be 0. And so we'll draw a little horizontal line at each of these 0 slopes. It's really helpful when graphing a slope field to begin by recognizing where the slopes will be 0. The slope will be 0 when when the numerator is 0. And so when x is 0, all those slopes will be 0. And we'll just put little horizontal lines there. How about when y is 0? Well, when y is 0, when y equals 0, the slope is undefined. And an undefined slope will go with a vertical line. So everywhere where the y is 0, there will be an undefined slope. It'll have a vertical slope. And so we've already got a lot. Look, we've already graphed 9 of these points. Let's do some more. What about, let's just pick individual points. This is 1, 1. When x is 1, dy dx evaluated at 1, 1 is going to be negative 1 over 1. 1 divided by 1 is 1. Negative of 1 is negative 1. So when x is 1 and y is 1, the slope is negative 1. So we're going to put a little negative slope there, a slope of negative 1. Notice that a slope of negative 1 is a 45-degree angle. It's going down by as much as it's going over by. A slope of negative 2 is more steep, so it's going down by 2 and over by 1. A slope of negative 1/2 would be going more flat because it'll be going down by 1 and over by 2. So what they're really just looking for on the AP exam is like, how are your slopes compared to each other? So let's look at like the point 1, 2. The point 1, 2, dy dx at 1, 2 is going to be x is 1 and y is 2, so negative 1/2. And what we should do is we should know that's flatter than this one. So it should be negative, but flatter. And so what they're looking for in the AP exam is, okay, are the slopes negative? Great. Is the one above it flatter than you made this one? Great. Do they need it to be exactly a slope of negative 1/2? No, they just need it to be like a little bit flatter. Okay, how about at the point 2, 1? What is the slope at the point 2, 1? Well, hopefully you got that when x was 2 and y is 1, we'll get negative 2 over 1, which is negative 2. And so that's going to be a negative slope, but it's going to be steeper than these. So I'm going to draw it a little bit steeper. All right, how about over here? What about at the point negative 1, 1? When you put in negative 1, 1, what is the slope? When x is negative 1 and y is 1, dy dx at negative 1, 1, the slope is negative of negative 1 over 1. Negative of a negative is positive, so we end up with positive 1. So at the point negative 1, 1, the slope is positive 1. So the slope needs to be increasing and at exactly like a 45-degree angle. We can kind of start connecting these, right? Like it's going to look kind of like this. I don't know. There's like a curve going like this. Let's connect. Let's find a point, and there's a vertical line here. Okay. Vertical lines everywhere there. How about at negative 1, negative 1? Well, when x is negative 1 and y is negative 1, the slope is negative 1. Negative, negative, negative. 3 negatives is going to end up making a negative. So this has a slope of negative 1. And we can kind of follow this curve and see what's going on here now. When x is 1 and y is negative 1, we'll get a positive 1 slope. And so we end up getting a circle. So by graphing all these slopes, like if we were to graph all these slopes, you would, I'm sorry, that's flatter. Yikes. You would get a sense of what these curves look like if you just follow the curves. And just by plugging in the x's and the y's, you can graph slopes at different points and see what shape it makes for the original function. So the solution to this is apparently a circle. That is the family of solutions is going to be circles. Let's see how we can solve that analytically using calculus and algebra. I think you'll prefer this better to slope fields. It goes a lot faster, even though this seemed like it took forever. We can do it a lot faster by solving. And the way we're going to do this is called a separable differential equations. There's actually a whole course on differential equations that you can take as soon as you finished calculus in college. It's really important for engineering stuff because so often we care about how things are changing in engineering. But the way separable differential equations work is we'll always have dy dx equals something. And what we're going to do is and this is kind of like an algebraic trick. It doesn't really have much meaning. We're going to multiply by the dx on both sides. And so we're going to end up getting dy equals something dx. And so what this is going to help remind us about is we want the x's on the right side, and we want the y's on the left side. Okay, so the way we're going to do this is we're going to move the dx over to here. So we're going to put dx, and we're going to have dy over here. And we're going to find a way to get all the y's to the left side. And you're always going to be able to do this using multiply, divide, and that's it. Like, you're allowed to multiply and you're allowed to divide. You will never use like adding or subtracting to move something to the other side, because you'll notice that this, when we multiply by dx, needs to be multiplying by something. And so we will always only use multiplying and dividing to get something to the other side. So we need to get these y's to the other side, and we're going to do it by multiplying by y on both sides because it's dividing by y. Okay, so we're going to get y dy equals negative x dx. And once we have the y with the dy and the x with the dx, what we're going to do is we're just going to do the integral of both sides. And we're going to do the integral of both sides with respect to their correct variable. So the integral, oh man, I should have checked and see if my pens worked today. Yuck, these pens don't work very well. Oh wait, I might have a pen in my pocket. I think I do. The integral of y dy is going to be 1/2 y squared. We're going to raise the power by 1, and it's going to have a plus c equals, over here, what do we get here? Well, this is, we raise the power by 1, and we divide by 2, so negative 1/2 x squared plus c. But these are both constants, and so we actually usually only write the c on the right side, because like a constant minus another constant is just a third constant. It's still going to equal a constant. And so it doesn't matter where you put the constant. And so the standard is to not write a plus c on the left side and only write it on the right side. So, so this is the first step to solving a differential equation, is to just do the antiderivative. And then we almost always want to solve for y. But before we do, they're often going to ask what the particular solution is. And we can solve for this at any point, and now seems like a really good time. They will give us an x and a y. We'll plug in x and y. So 1/2 of 1 squared equals negative 1/2 plus c. I'm going to add the 1/2 to the other side, the negative 1/2 to the other side, and get 1/2 plus 1/2 is 1. And so c is 1. And so I'm going to go and plug that in right here. So c equals 1. And I'm going to now solve for y. Go ahead and do that on your own. You guys can solve for y here. We can multiply by 2 on both sides to get rid of the, I'm just going to multiply both sides by 2 to get rid of the 1/2. So y squared equals, here when I multiply by 2, I'll get negative x squared. And this is a binomial, so the 2 needs to distribute. And then I need to take the square root on both sides. One thing to remember when you take the square root on both sides is that this is going to be plus or minus the square root. And what we're going to do is we're going to figure out whether it's positive or negative square root based on this. You'll notice that the initial condition is going to help us decide whether this is positive 1 or negative 1. Sorry, this is a positive 1, and so since y has to be a positive, this must be the positive square root. So because y is greater than 0, y is equal to the positive square root of negative x squared plus 2. If the initial point had been 1, negative 1, like we literally would have gotten the exact same c value and everything, we just would have needed to use the negative square root instead. And that's because we would have been on the bottom half of this circle, right? And so we would, like, this is actually negative square root of negative x squared plus 2, whereas this is positive square root. So depending on where your point is, what your initial condition is, it could be positive or negative square root. We need to be a little careful with that. So remember, if you take the square root of both sides, it's positive or negative, and we'll use the y value to tell us which one. So that's it. This was the equation that matched this differential, this was the particular solution that matches this differential equation. We solved for c, and I want to point out, like, we could have solved for c kind of at any point, but I think solving for c at the beginning is usually a little bit easier. All right, I want you guys to try this. We're going to try this on our own. And just really quickly, let's try, I want you to just try to graph on your own paper what these slopes are at these different points. So there's these 12 points. This was from an AP exam. They had you put the slopes on your AP booklet at 12 points. And here's the differential equation. And I hope you noticed that the slopes are going to be 0 where? Well, the slopes are going to be 0 everywhere x equals 0. That makes the slope equal to 0. So all the places where x is 0 are going to be horizontal slopes. Okay, now from there, there's still 8 more points to do. So let's pick like 1, 1. When x is 1 and y is 1, what's the slope? Well, when x is 1 and y is 1, we get negative 2 over 1, which is negative 2. So at 1, 1, the slope is negative 2. It's kind of a steep negative line. How about at 1, 2? I'm actually going to plug it in because I'm having a hard time like picturing it in my head. Okay, so when x is 1 and y is 2, we get negative 2 over 2, which is negative 1. And that's a normal slope of negative 1. So it's less steep than this one. That's what they're looking for, is just to see, is this one less steep? How about at 1, negative 1? Well, at 1, negative 1, we're going to get negative 2 divided by negative 1, and negative divided by negative is a positive. So we're going to have positive 2. And what about at 1, negative 2? At 1, negative 2, we'll get negative 2 divided by positive, oh, sorry. See, I really should write these down. Negative 2 times 1 over negative 2. A negative divided by a negative is going to be a positive. 2 divided by 2 is 1, so slope of 1. Somewhere over here, if you do them, you'll find that these have slopes like this and like this. And these ones have slopes like this and like this. And you can now see the shape it's making. It's making like an ellipse. This is apparently an ellipse, a vertical ellipse. This is the differential equation of what an ellipse would look like. So that's cool. I couldn't tell that just by looking at it, could you? Maybe. And this is a specific C value. There'd be another C value over here. Depending on what C it is, it'll make a different ellipse. And you'll notice these are not functions. There will be a positive function and a negative function. And depending on what the initial condition is, it'll either be the top one or the bottom one. So keep that in mind. Now, this is the big question that is always like the big part of the AP exam. Oh wait, no, not yet. Let f of x equals, let's read this carefully. F of x is the particular solution to the differential equation with the initial condition f of 1 equals negative 1. So when x is 1, y is negative 1. So right here, we already found that that slope was 2, right? Write an equation for the line tangent to the graph of f of 1, negative 1, and use it to approximate f of 1.1. So this is stuff we should be able to do. What is the equation of the tangent line? Hopefully we know that for the equation of the tangent line, we need a slope and a point. And they've given us that. So tangent to the line, 1, negative 1, that's where this is. So the point is x1 is 1 and y1 is negative 1. So it's going to be x minus 1 minus 1. And we need the slope. And to find the slope, we can use the derivative. And we already found it when we were doing this tangent line, but plugging in 1, negative 1, negative 2 times 1 over negative 1. So f prime of negative 1, f prime f prime at 1, negative 1 equals this. Oh, we should probably write that, label where this slope is coming from so we can get our points in the AP exam. Negative 2 over negative 1 is positive 2. And so we're going to get y equals 2 times x minus 1 minus 1. That's the equation of the tangent line. And it says to use it to approximate f of 1.1. So f of 1.1 is approximately equal to, we're just going to put in 1.1 into the tangent line. And you can leave like your answer like this on the free response portion of the AP exam. This was a free response question on the AP exam. 2 times 0.1 minus 1, 0.2 minus 1 is negative 0.8. Okay, so that is what f of 1.1 is approximately equal to. All right, find the particular solution. This is always going to be, guys, this is worth like 2 points, 2 points, 5 points. This is always worth a ton of points on the AP exam. I've never seen it be worth less than 4 points. Like it's a ton of points. Find the particular solution, y equals f of x, to the differential equation with the initial condition. So they'll give you an initial condition. This helps to find c. We want to find what y is equal to. We'll always get y by itself at the end, and we'll use this initial condition. So let's take our differential equation, and hopefully you remember what our first step is. Our first step is we move the dx over to here, right? We're going to put the dx over to this side by multiplying by dx, kind of. It's like the algebraic trick we're kind of using. And which side do the y's need to go on? The y's need to go on the left side with dy. And what are we allowed to use to move it? Only multiplication and division. So we can multiply y on both sides and get y dy, that'll cancel out this, equals, we just leave the x's alone over here. What is the integral of the left side? We're going to do the antiderivatives now. The integral of the left side is, we raise the power by 1 and divide by that power. Here, we raise the power by 1 and divide by that power. And we put a plus c. You get 1 point for separating the variables. So as soon as you've gotten all the y's on the left side and the x's on the right side, that earns you a point. Guys, these are like the easiest points in the AP exam to get. You can get them like, there's so many points you can get. Then this is usually worth either 1 or 2 points, depending on how hard the antiderivatives are. This one would probably be worth 1 point because these antiderivatives were pretty easy. So you get 1 point for doing the antiderivatives. You sometimes get a point for just writing the plus c, although sometimes, more recently, they've been giving you a point for writing the c and then using it. So now, after we've done this, we need to find c, okay? So what is c going to equal? Well, we need to use the initial conditions. So use the initial conditions. And this is what they're looking for on the AP exam. They're looking to see, did you use the point 1 comma negative 1? So when x is 1, y is negative 1. So 1/2 of negative 1 squared equals negative 1 squared plus c. So 1/2 equals negative 1 plus c. And when we add 1 to the other side, we get 3/2. Because when we add 1, we need to turn it to 2 over 2. That way we can actually add it with a half. We have to get a common denominator. So adding 1, 2/2 plus 1/2 is 3/2, and that's c. So we're going to plug that in. 1/2 y squared equals negative x squared plus 3/2. And now you need to solve for y. So we plugged in our c, and you need to solve for y. Guys, you can't get the points for solving for y if you didn't find c, because you won't get the right solution for y. So always make sure you're plugging in to find c. How do we solve for y here? We need to multiply by 2. And so we're going to get y squared equals negative 2x squared. This is a binomial, so it'll multiply here, and it'll multiply here. Multiplying by 2 and dividing by 2 will cancel out. And so we get y equals, remember to take the square root, we always do plus or minus the square root of negative 2x squared plus 3, because we could either be on the top half of this semicircle or the bottom half of this semicircle. It depends what our initial condition is. So let's look. Our initial condition is when y equals negative 1. And so in this case, y is less than 0. So the y needs to be this negative version of it. Y is negative square root of negative 2x squared plus 3. And that is our solution. So that's it, guys. You'll get some practice on these differential equations. They get, like, you're just using your skills you already have. It's not really all that new. The big idea that is different is you're separating. So the steps we will do, I'm just gonna write them out right here, is 1, separate variables, y on the left, x on the right, and the dx will always be here and the dy will be here. Guys, it doesn't have to have y and dy. It could say like y prime equals whatever. But if you want, you can always change y prime into dy dx and move the x's to the right side and the dy to the left side. Like, it's fine to rewrite this. Another thing you could do though, like, let's say it's y prime. I just want to show you this real quick. Let's say it was like y prime equals x over y. Actually, I want to show you a different one. Y prime equals y over x. So again, the y's are going to go to the left side. Remember, it's important to separate this. So this is y times 1 over x. And we need to move this to the other side. We're going to divide by y in this case. So we're going to divide by y. And we wouldn't leave it like this. We want the y prime to be separate. So it's 1 over y. I'll put this down here. 1 over y times y prime equals 1 over x. And what you'll notice here is this kind of looks like a chain rule, which is fine also. Like, there's more than one notational way to write it. Like, if you don't rewrite this as dy dx, you're still okay. You won't like lose points on the AP exam. Like, you could do this, but if you left it like this, you wouldn't lose any points. I just wanted to make sure. So that's separating variables. 2, integrate both sides. 3, solve for C. 4, use initial conditions, I guess, to do that. Initial conditions. Solve for Y. And all of these are going to get you points, guys, along the way. This is one of the sections that even if you did badly on a few different things this year, like let's say you don't remember related rates at all, this is worth, this free response problem will be worth more points than all of the related rates on the test. So just and it's not hard to get good at. So that's what we'll be doing over the next few days. This is the section that really usually bumps a bunch of people who are on the edge of passing the AP exam to passing the AP exam. So guys, that's it for today. Do a good job on this unit because it's some really easy points to get on the AP exam and it can bump you up to passing.